Muchas gracias para la invitación y la introducción, pero voy a hablar en inglés. Buenas tardes. So I have been working for almost 20 years now in the field of spinal cord injury. And what I'm going to start with is a summary of 10 years, actually, of this research with one video. This is a rat that received a severe spinal cord contusion. That's somehow mimic what you would observe in people with spinal cord injury. So you have this very severe contusion that will spare maybe 5 to 10% of descending fibers. You can see them here, and now we have the ability to visualize in 3D in uncut tissue all these descending fibers, and you see that there are some spared fibers, so anatomically present, yet functionally silent, meaning the rat is trying to activate the muscle, but it's completely paralyzed. So to reactivate the spinal cord, we apply electrical stimulation. This will have two effects. First, the spinal cord will be able to process sensory information, meaning the rat now is working automatically. The spinal cord is reactivated. The second effect is, you approach delicious chocolate from Switzerland, and then the rats get excited. The residual descending fibers are becoming functional. The stimulation enables these anatomically intact yet functionally silent fibers to actually modulate the spinal cord so the rat can jump. But if you remove the chocolate and she gets frustrated, the brain can also completely stop this automated locomotion. So basically, the stimulation is restoring the communication between the brain and the spinal cord below the injury. And then before jumping towards human application, we wanted to understand really the mechanism to have the best possible application towards humans. So we did a lot of work going back to the preclinical model, and actually started with computers. So I have this good friend, Silvestro Micera, and this very talented postdoc, Marco Capogrosso, who built this finite element model to understand what is the electrical field induced by this stimulation. So now we just stimulate the dorsal aspect of the spinal cord. And what we found is that this electrical field, as you see, does not penetrate the spinal cord. It actually flows around the spinal cord in the CSF. Meaning, this electrical field will activate the neural structure with the least resistance to current, meaning the thickest fibers running in the lateral aspect, and these are the proprioceptive fibers, right? They have a lot of myelin, so they are very easily depolarized by electrical current. This was a prediction of the model. So to really show this mechanism, what we did is we recorded these proprioceptive neurons in the dorsal root ganglion neuron. So you can see here, we can really visualize this whole spinal cord in 3D. You see these nice bundles of proprioceptive fibers. Here they are labeled genetically. And we can record all the cells in the dorsal root ganglion. So you see here how they are activated with the stimulation. And this is performed in a transgenic animal that expresses a fluorescent protein in proprioceptive neurons. So here I show you the activated cell. And if I superimpose the signal from proprioceptive neuron, you will see that all the cells that are activated are proprioceptive. Then what is the mechanism? How does it work? Well, this stimulation activating proprioceptive fibers will have two effects. The first is that you see like this massive innervation of the spinal cord by the proprioceptive fibers. So when normally the descending input or the sensory information, they will fire, but because of the low level of excitability of the spinal cord network, you don't see any effect. So the system does not fire, you see no muscle activity. But if you apply this electrical stimulation, because of the widespread connection of proprioceptive fibers, now the same input from the brain or from the periphery will enable the network to fire. So that's increased excitability. The second mechanism is that, of course, proprioceptive fibers are connected to motor circuits, indirectly or indirectly activating motor neurons. So each time you're going to send one pulse of electrical stimulation, what you will observe is a response in the muscle. So one pulse, you activate mono and polysynaptic reflex responses, and you can record this reflex in the muscle. In neuroscience, now we have a lot of fancy tools, so we can shut down specifically these proprioceptive neurons. Here we use chemogenetics. Basically, we express a receptor only in proprioceptive neurons. And then we can silence this neuron reversibly within minutes. If we do this, we apply the stimulation, and you see that the reflexes are gone. So this is really the pathway that we are utilizing. And then how does it work? Well, no, if you look during walking, this is a wild-type animal with a stimulation. She's walking continuously. And if you look within the muscle activity, you will see that there's a succession of extensor burst in stance, flexor burst in swing. If I zoom in within this burst, you will see that they are elaborated with a succession of these reflex responses, which are logged to each pulse of stimulation. So this is how we are activating the motor system with the stimulation. One, increasing excitability. Two, recruiting the muscle through proprioceptive circuit. And indeed, if the animal has absolutely no functional proprioception, we can stimulate and we observe the best example of paralysis. Absolutely no effect. Why is it important? Well, now that we really understand the mechanism, we can operate a transition from this continuous empirical stimulation to a more targeted approach, meaning try to reproduce using proprioceptive pathways the way the brain will activate the spinal cord naturally in order to walk. With the caveat, which is, what is the natural activation of the spinal cord during walking? To do so, we went back to basic electrophysiology, so you know the classic representation of electromyographic activity, EMG, during walking. This is a healthy person, so you have these nicely organized sequences of recruitment of leg motor pools. And you know very well that there is a clear organization in the spinal cord of the motor neuron colons. So we know more or less theoretically where are these different cells. So we can represent the activity of the motor neuron directly onto the spinal cord. So you kind of create this spatio-temporal map of motor neuron activity. And you see like these hotspots associated with swing, stance, propulsion, which is exactly what you want to reproduce to have the best facilitation of walking when you stimulate the spinal cord. To do that, you need a very specific, spatially selective stimulation. So here we have at EPFL, in our school, Stéphanie Lacour, she's an expert of stretchable electronic. So this is a silicone membrane with a stretchable track, stretchable electrode. The whole device is stretchable, so it can resist for a very long time. And it brings this specificity, meaning the ability to really access the different posterior routes to modulate the different region of the spinal cord. It needs to be super precise. This is why we like to talk about the Swiss watch precision, because it's 20 millisecond precision to do this kind of work. The animal is paralyzed. You apply the conventional continuous stimulation, the animal walks. But it is 1 week after the severe contusion. So the animal at some point will collapse. This is when we turn on this spatio-temporal stimulation, so targeting the posterior roots. They're going to target the activation of motor neuron associated with stance, swing, left leg, right leg. And you rescue walking and really increase the vigor of the locomotor movement. And then if you continue training with this type of stimulation, what you observe eventually is a neurological recovery without electrical stimulation. Here the rat, severe contusion, non-trained, dragging his body along the runway. And the animal now, after training, there is no stimulation, no body weight support, but you see some deficit still, but he clearly is able to carry his body and even control some balance. Then you ask, how is it possible? What is the underlying mechanism? So I'm going to just summarize in 2 slides, but what we found is that this paradigm that with reactivating the spinal cord below the injury with this willpower training encourages the central nervous system to build new connection. And you find them, one, in the brainstem. So you see here this 300% increase in the density of motor cortex projection in the brainstem, specifically in the gigantocellular nucleus, because this is a key region for walking. And why you have this increased density? Because the cortex will go through the brainstem as a relay pathways to access the lumbar spinal cord below the injury. Because now if we look at the level of the injury at these reticulospinal fibers coming from the ventral gigantocellular nucleus, you see that many are interrupted by the contusion, but some are spared. And what happens is that these spared fibers, they sprout. You have 1 to 5-fold increase in the density of these glutamatergic fibers in the key locomotor region. So this is the underlying mechanism. You're actually inducing plasticity, no regeneration, but reorganization of spared pathway to enable the rats to regain walking. But the question is, can you translate this now from the sophisticated environment of the laboratory to the clinical settings? And for this, my dear colleague, Professor Jocelyne Bloch, a colleague functional neurosurgeon, will talk to you about this work.
Excelente presentación. Jocelyne?
Yes. I present now the human study. So when I met Gregoire 7 years ago, he had done all his rodent work and asked me if we could do the same in humans. And of course, all of you know that it's not just an increase of size. There are a lot of other challenges to implant devices in a human and to make it accepted by the doctor and regulatory people. So one of the first challenge was the hospital. So we had to create the same kind of environment as the one that was done for the rats. So the very technological area with a lot of possibilities to record, to train, a huge room, and this was the first challenge. And the second challenge was the implanted device. So from the stretchable electrodes we had in the rats, we had to go to something that was robust and that we could implant a human, and we decided to work with the Medtronic. So with the leads, that is the 565 lead, 16 electrodes, that was not exactly the one we wanted, but we thought for a first approach it was good. But then, and Gregoire's team could convince the people in Medtronic, Minneapolis, to hack the system and to be able to control it in real time. So that's not very easy. As you can see, there is a chain of communication, infrared, Bluetooth, and then electromagnetic induction that makes it pretty complicated, and it's not something that everybody can do easily for now, okay? So we decided also that after having modelized the spinal cord of the different patients, that probably this 565 lead was not the most appropriate one, because for us it was very important to reach the targets, the proximal targets and the proximal roots and the distal roots to be able to walk. So from L1 to S1, and the 565 lead in most of the patients is too short and a bit too thin. So that's why we decided to found a started company, GTX Medical, to start thinking about the next generation of leads. And here you see what it looks like, the new lead, and we've implanted the first patient. I'll show you after that. But you see that the array is much longer and a bit larger, and also we'll have to think about all the system that it's much simpler to be used. So you see here one patient who has been implanted and who is completely paralyzed. So the stimulation is off, and you ask him to stretch his leg. And as you can see here, it's impossible for him to do it. So now you switch on the stimulation at an area where you activate the L4 roots. So you want him to stretch the leg. But you don't ask him, you say, don't do anything. And you see that if you switch on the stimulation and the patient does not want to do it, nothing will happen. But now if you ask him to stretch the leg, he's able to do it. So it means that his brain is still activating, and probably through these silent fibers Gregoire spoke about previously in the rats. Now these silent fibers are able to express themselves and to be rewarded by movement. So then the next challenge is you cannot just do small movement and muscle activation. Then to walk is much more complicated, so you have to stand up. And the program is to deliver bursts of stimulation at the different spots of the spinal cord in order to activate the different muscles and to mimic walking as natural as possible. You have to do it physiologically. So here, I'll show you one of our first patients, David. So when you switch on the stimulation, he walks, and then you stop stimulation, and then you see that he's unable to walk. And if you switch on again the stimulation, he'll be able to walk. So this patient had a cervical spine injury, and he was completely paralyzed on the left leg and able to move a little bit on the right leg. And you'll see here, if you ask him to do a step of a different height with the same intensity of stimulation, he'll be able to modulate the height. So here you say, exaggerate your left leg, exaggerate your step. Remember that he was completely paralyzed on the left. And he's able to modulate with the same intensity of stimulation, meaning that the brain is still able to do this modulation through these silent fibers and with the activation of the system. So we tried to compare the continuous stimulation with the targeted stimulation, and we saw that that was quite obvious that in the targeted stimulation, way of stimulating, David was able to walk much better than if we did the continuous stimulation. 6 of our patients who were implanted could walk with this stimulation, and you see some of them are very severely affected, some of them less severely affected. They're all generally between B and D. But all of them have a personalized program and can walk with this robot, helping them, depending on the severity, to have more or less weight. And then with this possibility of walking, they can train. And training is very important. So you'll see here with the new lead that we've developed, this is our first AGA patient who 1 week after the implantation is already able to walk with this new lead that is able to reach really well all to target all the routes that are necessary to walk. But he is also able now to train. And all of our patients have to train intensively. And that's the key of this therapy, is to train 4 or 5 times a week and to walk a lot. So it's a lot of efforts. They're athletes and a lot of will. So at the end, when the more they go, the more they change, the body changes. And David, you remember this patient who had this cervical injury, who was completely paralyzed on the left leg, after 2 months of training, came to the clinic and showed, without stimulation, some movement of the left leg. And 5 months after the training, the intense training, you see that he is able to completely stretch the left leg without stimulation. So after 6 months of training, you see that he's able, without stimulation, to walk between 2 parallel bars, and that's something that he would never have been able to do before. So it means that there was a plasticity, that something happened. Of course, I cannot show you the increased density of neurons and the sprouting, but we can imagine that the same mechanisms happen. So when you see him, you say, good, but it's not perfect. And of course, he prefers walking with stimulation on. So that's why we received the authorization to use the stimulator outside from the laboratory. And you'll see him with a system that can be activated with a voice control and a watch, and that enable him to walk outside and easily activate his stimulation system.
Stim on.
Okay, start message sent to implant.
So all of these people used the stimulation system outside of the lab, but for different activities. So you see another of our candidates who loves doing bike. He has a trike because it's a bit difficult to do a regular bike for him. And you see that he's able, with, again, stimulation and a feedback, to ride his trike. You see the motion feedback. And here, with a tablet that is able to activate the spinal cord, and he's able to go. And here you see another of our candidates who loves to go to the gym. He's completely paralyzed. He has no motor control of his leg, and when he switches on his stimulator, he's able to lift up to 40 kilograms. and he's very happy to do it. So you see, those are all our candidates. Until now, we've implanted 8 of them. So 7 with the regular lead of Medtronic, 1 with this new lead, and all of them have a lot of changes in their body, in their activity, but 8 is not so much. And with the system we are implanting, we know already that it's not something that we can deliver to all the world easily, because it's a technology that is difficult. So we have a lot of things in mind. First of all, as I told you, we want to develop this new system, but we also want to show that it's better probably to start earlier, in an acute phase, to implant the devices earlier, because we know, as Gregoire said, that if you do it early after the injury, probably the results will be much better. So we'll have this multicentric trial, and we'll do it with a new system that has been developed now with GTX Medical, that is another new neurostimulator that is going to be much easier and much more practical for everybody. So for the future, as I said, not only we want to diffuse this therapy to more people, more patients with paraplegia, but we also, Gregoire is going to show you also what we have in mind for the future, the different advances in technologies and other applications.
So just in a few minutes, I would like to make you dream a little bit. And they will prepare, ideally, José Carmena's presentation. Because, Jocelyne showed you that, we control the stimulation in real time. So what it means is that you need a signal to synchronize the stimulation with the intention of the patient. The way we do it currently is with camera or with some, as you have seen, some IMU, so inertial measurement units, accelerometers located on the feet, etc. Great. But what if we do like Niels and José and just pick up the signal directly from the brain? That would be the best way to do it. So that's what we have been doing in collaboration with the VIS Center. So using exactly the same electrode that Niels showed you. So put this black rock, so 96 electrodes in the leg region of the motor cortex, decode motor intention, which in locomotion is very simple. Stand, swing, stand, swing, stand, swing. And then we send this signal wirelessly to exact same stimulation system that you have seen from Medtronic that we use in patients. Here, Jocelyne performed an hemisection of the spinal cord, so it's transient paralysis of the right leg. It's only 6 days after the injury, so you see the right leg is completely paralyzed. And without any training, just 2 minutes training the decoder, turn on the digital bridge between the brain and the spinal cord, and you see that immediately the monkey is having this nice stance swing movement. You turn it off, and then his leg remains paralyzed. So this is very, very robust. And it's something easy to do. I mean, you can even use it in humans using an EEG system. So we have been doing some preliminary work like this in humans in order to prepare a clinical trial with more invasive technology. But here, this is one of our completely paralyzed individuals. We do EEG recordings to decode his intention to do this stretch, which I would call an extension of the leg. And we link the decoding here proportionally to the stimulation. So the more you think about doing the movement, the more you're going to stimulate his spinal cord. And you can see here how it's actually very robust. He does it all the time. It's like, think about it, and he has this very nice control leg extension. So then the next step for us will be to go to human. But in parallel, we thought, what are we doing here? Connecting a healthy brain with a reasonably healthy spinal cord, but there's a problem of communication between the two. That's spinal cord injury. There's a physical interruption. But there are also other neurological disorders where you have a problem of communication between a reasonably healthy brain and the spinal cord. One of them, for example, is Parkinson's disease. And you know that we still have a lot of issue with gait disorder in Parkinson's disease in the last stage. So we ask, can we use the exact same technology approach to improve gait in Parkinson's model? So, in primates, you have this MPTP model of Parkinson's disease that really replicates the key hallmark of gait disorder in Parkinson's disease. So you see like this freezing, bradykinesia, and if we analyze precisely the kinematic, you will see, or you have these short steps, low step height, and this very slow movement, right? This is a monkey before and after the PTP treatment. And then if you want to have a brain-spine interface, you need to be able to decode motor intention from brain activity. And there have been a lot of publications that showed disrupted motor cortex activity in people with Parkinson's disease. Well, at least a lot of beta bursts emerging sometime during locomotion. But is it true that this disrupted motor cortex activity prevent from decoding locomotor state? So we asked this question in our model. And then what we did is apply this decoding algorithm that José will show after, that look at the structure of the neuronal population firing. And then what you see that before versus after, you have no changes. So the motor cortex is really firing in the same way, despite, as you see, the ongoing deficit in the kinematic. So there's a lot of deficit because the basal ganglia has disrupted the command going downstream, but the motor cortex is really trying to do the same thing, meaning that for us it's very easy to decode the intention and link it to the very healthy spinal cord. So here this is one of our primates with, if you know the score, it's 11 on the scale of motor disorder. So you see it's very Parkinsonian. And without any training, again, it's 2 minutes only to train the decoder, turn on the brain-spine interface, and you have this immediate increase in posture and in alleviating many of the gait deficits. I'm going to show you another monkey, even in a more complicated task, because here it needs precision power placement along the rungs of a ladder. So you will see classical Parkinsonian gait. He's missing the rung. He has some tremor. It's very slow movement. He put both feet on the rung because he has a problem of balance. And then, without training the monkey again, the commands are like integrated together, like the stimulation and his intention to put the leg sufficient to regain this precise power placement and fast progression. So now we have several monkeys like this. And what is nice also is that it works very well with deep brain stimulation. So you have a synergy between both intervention and they can operate together. So this is the first step. But in the big picture, what we would love to do with Jocelyne is to bring this technology to people, not only the spinal cord stimulation, but also have this brain implant in order to have a much more seamless utilization of this neurotechnology to regain movement, but also to train the people, closing the loop. I'm sure José will talk about it after. And the idea that eventually this technology needs to become so easy to use that patients like David can just walk to their office drinking their coffee. Still a dream at this stage, but I think this is a great time to be a neural engineer and a functional neurosurgeon because we're going to make it happen. Thank you very much.